Okay, now let's continue our discussion on the principle of virtual work and extend it to the principle of virtual forces. The principle of virtual forces, or PVF for short, it works almost in identical fashion to the principle of virtual displacements that we've just seen in the previous presentation, but except now it works in the other space. So let's consider, for example, again, a linear elastic system that deforms up to displacement delta sub 0 when we apply a force of magnitude F0. The complementary work in this particular case is equal to the shaded area in color blue and denoted here with W sub 0 star. Please also note that because this is a linear elastic system, this is precisely equal to the actual amount of work that we have done, which we previously discussed, and that would be W sub 0, the area of the triangle shown here in color yellow. Okay, so now we're again in equilibrium position, and this time instead of perturbing the deformations by an arbitrary amount, we're going to perturb the forces. When we do that, we're going to keep the displaced deformed state constant, just like what we have done in the principle of virtual displacements, in which case we had kept the force system constant and only perturbed in a virtual manner the displacements. Here we are keeping the deformed shape constant and perturbing the forces, external forces, by an arbitrary amount, here denoted as a delta F. This discussion is obviously extendable to material points when we consider, for example, a material point on which a stress state sigma 0 is acting, and it caused it to deform by an amount of epsilon sub 0 strain, and there the complementary internal work would be energy density, complementary density would be denoted here with U superscript star sub 0 bar. And again, the perturbation works there the same way. We would keep the deformed state constant and perturb the stresses. So in our quest to make principle of virtual forces something useful for us, we would need to compute the internal complementary virtual work. Let's assume that we're going with the material point symbolism here. The internal complementary virtual work density would be simply computed by taking the inner product of the perturbation to the stress vector or tensor and the strain, the real strain tensor or vector. And if we integrate all of that over the entire volume of the object that we're dealing with, that will give us the total complementary virtual work. We can rewrite the statement slightly differently by using the constitutive law, which here we are assuming to be the linear elastic constitutive law that relates the stresses sigma sub 0 to the strains through the material stiffness matrix. We can restate that constitutive law by inverting the material stiffness like that, and we would make that substitution for the strain into the integral we have above, and we can write it in this particular format where the internal complementary virtual work can be computed using the stress in equilibrium, which is sigma sub 0, and the arbitrary perturbation to that stress del sigma 0 only. So let us now take this expression and then with this state the principle of virtual forces. We would just simply say that the complementary external virtual work done by arbitrary perturbations to the force system that is in equilibrium should be equal to the amount of complementary virtual work stored internally in the system. Another way of saying the same thing is as follows: the strains and displacements in a deformable system are compatible and consistent with the constraints of that system if and only if the external complementary virtual work is equal to the internal complementary virtual work for every system of virtual forces and stresses that satisfies the conditions of equilibrium. This is obviously a mouthful, but it will work in the same way as the principle of virtual displacements did, and will give us solutions for statically determinate as well as indeterminate problems in a very practical manner. Consider, for example, a cantilever beam. Let's assume that this cantilever beam is deforming under some externally applied forces, which are not shown here. But let's assume that we would like to find out the tip deflection at node 1 of this cantilever beam. To do so, we will have to apply a virtual force in that direction by an arbitrary magnitude del f sub y1. From this, we will be able to compute the external complementary work, and ultimately we would have to compute the same thing using the internal forces. And once we equate the two relationships, this will give us a useful expression from which we can extract the unknown displacement at node 1. And in doing so, we will have to obey certain rules. The virtual force systems that we have chosen to our advantage have to satisfy internal and external equilibrium conditions. Case in point, the shear diagram for this particular choice of the virtual force system is as follows. It's just a constant. And the corresponding moment diagram, which we will eventually, as you will see, use to compute the internal complementary virtual work, is a linear one. And this, the one that I'm showing you here, the moment diagram, is indeed compatible with the virtual force system that I have applied externally. Sometimes people make the mistake of using moment diagrams that are not consistent with the force diagrams or the shear diagrams, and then it would just produce an inconsistent system, and the principle of virtual forces will not work then. Consider, for example, a virtual moment diagram, which is incidentally 0 at the tip end when x is equal to 0, but it's quadratic. And if you use this virtual moment diagram to compute the internal complementary virtual work, it would not be consistent with that virtual force system that we see on the left-hand side, because internal equilibrium on that moment diagram, del mz, would imply a linear variation, whereas our shear diagram is constant. So this is a simple rule. When you apply a virtual force system, you need to compute the corresponding internal moment diagram or internal force system diagram consistent with that application of forces. And only then and then you can use the principle of virtual forces to your advantage. So this particular application that we see on the left side with a constant shear diagram and a corresponding consistent linear moment diagram is going to work, whereas the constant shear diagram will not work with the quadratic moment diagram, for example, as they are not compatible with each other. We can apply the principle of virtual forces to statically indeterminate systems as well, and this application then would work in the same way as the Castigliano's second method worked, because first, if we are dealing with an indeterminate structure, we'd have to create a determinate version of it, and we could do that by releasing an adequate number of degrees of freedom. And once we have done that, we can apply onto that system a virtual force system and then compute the corresponding internal forces, internal complementary virtual work, as well as the external complementary virtual work. When we're doing so, obviously for indeterminate systems, we have more than one choice in generating virtual force systems. So acceptable moment diagrams, for example, would be as follows. Here are three examples of it. The one at the top is consistent with a statically determinate version of the system that is simply supported on both ends. One that is cantilevered on the left side and free on the right-hand side. But also we could consider even a statically indeterminate virtual force system. And for example, the one at the very bottom corresponds to a version of the system that you're seeing above that is fixed on the left-hand side and simply supported on the right-hand side. This is also an indeterminate structure, but with this virtual force system, we might be able to, for example, compute not only the mid-side deflection in one shot, but also perhaps the unknown moment reaction on the left-hand side. So the principle of virtual forces is quite flexible and will produce very practical solutions for us if we are able to pick a good, useful virtual force system. Of course, to complete the task, we would have to still examine the equation that we see here on the right-hand side in the blue box, with which we can compute the internal complementary virtual work. So how does that integral work, for example, when we have flexural loads? For that, we need to figure out what sigma components we would have. We would, of course, have only one sigma component that would do any internal complementary virtual work. That would be sigma xx, and that is related to the external moment mz, or the internal moment diagram mz as follows: minus mzy over izz is that sigma xx, and likewise the virtual stress sigma xx, del sigma xx would be equal to simply minus del mz times y over izz. The third and last component we would need to compute that integral would be C inverse, which in this particular case would be just 1 over e, the Young's modulus. And once we plug in these three terms into the volume integral we have and split that volume integral into two parts, a part over the cross-sectional area and a third part over the length of the member, the beam, dx, we can re-express that same integral as follows. So I pulled out the terms that are not dependent on the cross-sectional area to the outside, which are del mz and mz itself. They'll be divided by izz squared. The two negative signs we had would cancel each other out. Of course, 1 over e in a homogeneous cross-section can also go outside the area, which would then just leave us with the task of computing the integral of y squared over the cross-sectional area, which itself is nothing other than izz, which would then simplify into this form. One of the izz's would cancel in the numerator and the denominator, giving us an integral of the product of the virtual moment times the real internal moment, which we may not completely know in case of an indeterminate system, but that's not a problem necessarily, divided by the flexural stiffness of the member. So if we can compute this integral, this would have given us the internal complementary virtual work, and by using its equality to the external complementary work for all arbitrary variations in the virtual force system, we will get useful results. We will get useful information. The same expression that we see here for the internal complementary virtual work can obviously be written as the work done by the virtual moments over the curvature distribution of the beam. What happens when we have axial loading? Of course, in axial loading, the stress also has a single component, and it's simply equal to the internal axial force Fx normalized by the cross-sectional area. The virtual counterpart of that will be as follows. Again, the material stiffness or material flexibility is 1 over e. Once we plug in those terms into the volume integral we have and carry out the cross-sectional area integral on the inside, we will have this result, and where we have used simply that dv is equal to a times dx, and that would just be the integral that we would have to carry out for the axial loading case. When we have torsion, we can work out the details as we have seen before when we discussed torsion, but the internal complementary virtual work can be simply carried out by taking the product of the virtual internal torque with the real torque divided by the torsional stiffness Gj of the system integrated over the entire length of the member. So let us look at some examples where we can compute, for example, analytical solutions using the principle of virtual forces. Let us consider an axial member that is subject to a real valued force of F sub x2, which causes then a displacement of u2 at the right node. The left node is fixed. And let's assume that we would like to find out, for example, what the displacement u2 is at the right node. What we will then have to do to the statically determinate system is to apply a virtual force at the location where we want the displacements, where we seek the displacements, which would then be simply that. At node 2, we will apply a virtual force of magnitude, arbitrary magnitude del fx sub 2, or del f sub x2, and then the corresponding internal diagram will be just as constant, with which we can compute the internal complementary virtual work as follows. The integrals are quite simple here because both del fx2 and fx2 are constant over x. So then the integral of dx over the length will just give us the length. and the internal complementary virtual work therefore will be this simple expression. And this expression should be equal to the external complementary virtual work for all variations of del fx2, for all possible values of del fx2. And the external virtual work is obviously merely del fx2 times the unknown displacement u2. This means that the relationships in the box, yellow boxes, must be equal to each other, which then tells us that u2 must be equal to simply f sub x2 times L over EA. As a result that we very well know, obviously, but this simple example demonstrates that the principle of virtual forces does work. Let's take a look at a little bit more elaborate example. Here we are again dealing with a determinate system, a simply supported beam. Let us assume that we're interested in, for example, computing the midspan deflection. We can compute the midspan deflection by simply applying a virtual force at the midspan of magnitude, say, del P sub c, which is arbitrary. And this would give us an internal moment diagram, the real moment diagram as follows, a bilinear diagram, which peaks at the midpoint, and the corresponding virtual moment diagram for the virtual force that we have applied, which was incidentally applied at the midspan, is equal to that. And to compute the internal complementary virtual work, we'd simply have to evaluate the integral. We can evaluate the integral by splitting it into two parts, and because the integral is symmetric about the midpoint, we can simply carry out an integral of del PC times x over 2 with PC times x over 2 from 0 to L over 2, and multiplying that result by 2, and of course normalizing that by the flexural stiffness of the member. And the integral then simply becomes del PC times L cubed over 48 EI. And if we equate this to the virtual work done by the external virtual work done by the virtual force that we have applied at midspan, which is simply del PC times VC, the principle of virtual force that says these two quantities must be equal to each other for all possible values of del PC. That tells us that the midspan deflection is simply equal to PC times L cubed over 48 EI, which is also a result that we know how to compute in different ways. But as you can see, this calculation was quite straightforward and simple to do and gave us an analytical result. We can use the same approach to, for example, calculate the deflection at the third L over 3 position of the same simply supported beam. How would we solve that problem? Well, we would solve that problem by applying a virtual force at that spot at L over 3 of magnitude, arbitrary magnitude del PC, and computing the product of the corresponding virtual moment diagram with the real moment diagram that we see here. And if we carry out that integral and equate the external to the internal, we will get the deflection at that spot. Let us now move on to a little bit more elaborate example where we're still looking at a simply supported determinate structure, but we're, for example, interested in calculating deflections at joints 2 and 3 using the principle of virtual forces. And since this is a simple problem, we can actually compute the exact solution and compare the results that we get from the principle of virtual forces and see if they are equal to each other. So we can directly write the internal moments with respect to the external forces that we have applied, because this is a determinate system. There are no unknowns in that case, and the MZ can be written in 3 segments. A formula for the segment of the beam from 0 to L over 4, another formula for the mid segment of the beam from points 2 to 3, and another formula from point 3 to 4. Please check the veracity of these moment diagrams for the statically determinate system. And now we'd like to, for example, compute the deflection at joint 2 and 3. For computing the deflection at joint 2, all we have to do is apply a virtual force of arbitrary magnitude. Let's call it just -1 for the sake of the argument here at point 2. And we can do the same thing by applying a virtual force del P3 at point 3. If we just look at the virtual force system 1, we will get a bilinear moment diagram for that when we apply it alone by itself. And the bilinear moment diagram will then give us the moment variation between points 1 and 2, as well as between points 2 and 4, for which, for the former, the x ranges from 0 to L over 4. For the latter, x ranges from L over 4 to L. And then we can simply take the product of this internal moment diagram with the external, the real moment diagram, mz, through the integrals that we have discussed. And of course, we have to deal then with 3 integrals for the 3 segments of the beam. And once we carry it out, we will obtain a value that is a function of P2 and P3. And that then tells us that the V2 must simply be equal to minus L cubed over EIZZ times the expression that you're seeing in parentheses. So this example was taken from your textbook, and there the lazy thing was done by setting the del P2 equal to -1, but you can just keep the arbitrariness of del P2 and carry that term in your integrals with which you compute the internal complementary virtual work, and it will just yield the same result when you insist that the external virtual complementary virtual work is equal to the internal one for all possible values of del P2, for example. We can do the same and repeat the procedure for the virtual force system number 2, and then you can compute through the same result, through the same approach, the deflection there. As you can see, these deflections would have been really difficult to compute by other approaches. For example, if you wanted to just express the fourth order ordinary differential equation for the simply supported beam and impose continuity conditions, or perhaps even use the delta functions to represent the concentrated loads, you'd have to do a lot of algebra to compute the deflections that are sought here. And the principle of virtual forces just provided us with means to compute them really quickly and easily. So this completes our discussion on the basics of the principle of virtual work, which we have examined in 2 different ways. We first of all discussed how the meaning of the principle of virtual work and how and why it worked in the context of rigid as well as deformable bodies. Then we have extended it to our discussion to the principle of virtual displacements and the construction of exact solutions using the principle of virtual displacements. We've then talked about the construction of exact solutions using the principle of virtual forces. In the following lecture, we're going to be talking about the use of the principle of virtual displacements for the construction of approximate solutions. And that is going to incidentally form the basis of the finite element method, as well as an alternative derivation of the direct stiffness method that we have seen previously.